Okay, so we will start. Sorry for the delay, everyone. So this is the February FPGA seminar. We have a couple of papers that are a preview of what will be presented at the FPGA conference. And they're both work from Greg Steffen's group. We'll start with Eric Forrest.
Thanks. So let's see here. So this is Octavo FPGA-Centric processor architecture. I'm going to be presenting this at FPGA 2012 later this month. So the driving motivation for this was easier FPGA programming. We decided, there's many approaches, but we decided to do overlay architectures, basically soft processors. So we had NEOS, the microblaze, a bunch of vector processors that were developed here at UBC and elsewhere. So these have a common characteristic of having inherited their architecture from their ASIC counterparts. They look like existing processors, which is good because we can use existing software tools to program them, makes them very easy to use, but there's a performance penalty to doing that. And basically because architectures developed in ASICs are a poor fit to FPGA hardware. ASICs are not FPGAs. ASICs gives you raw transistors, polys, vias. You can arrange them in any width and any which way you want. While an FPGA gives you fixed blocks of lookup tables, block primes, DSPs, and they have fixed widths, depths, and other discretizations. So this seems to suggest that there should be room for an FPGA-centric processor design. So that is really a special case of a more broad question: how do FPGAs want to compute? How do we express computation efficiently on an FPGA, as opposed to simply considering an abstract substrate you just map hardware to? So we can look at it, we can get an idea of what's necessary, what's involved, by just looking at the hardware on a Stratix IV, its width and its frequency. So Stratix IV gives us, DSP blocks. They can do a variety of functions, 36 bits wide at a speed of 480 megahertz. We got block RAMs, which can be up to 36 bits wide at a speed of up to 550 megahertz. We have the adaptive lookup tables, gives you 1 bit of output. They can run it up to 800 on the fastest speed grade. But then you take all that, you map a NEOS 2F, which is the fastest simple scalar processor known. It's 32 bits wide, and it runs at 230 megahertz. So there's a mismatch here between what the architecture of a MIPS like NEOS does and the underlying hardware, because we're obviously leaving a lot on the table. So we want to ask, as a specialization of how do FPGAs want to compute, what processor architecture best fits the underlying FPGA? So we tackled that with guided by some research goals. So initially, we wanted to assume threaded data parallelism. Think OpenCL, lots of separate data, lots of separate threads. We want to run at maximum frequency. We want to run as fast as the hardware will let us go. But we also want to have high performance. So even if we have a high clock frequency, we don't want to spend many cycles doing a simple operation, or have to spend many operations to do one thing. We never want to stall for memory. We never want to stall for data dependencies. And we want to aim for a simple minimal instruction set architecture. We don't want to just assume one and then carry it over. We want to start from scratch and see if we can construct something that's a better match. We ultimately always want to match the architecture of the underlying FPGA. So having worked on that with these guiding principles, we got a result. And we call it Octavo. It's basically a soft processor, 10 pipeline stages, runs 8 separate threads, and can run, in most cases, at the limit of 550 megahertz on the high-end Stratix IV FPGA. This is as fast as the hardware will let us run it. It's actually also a family of designs. It's not just one special case. It works well over a large range of word widths, 8 to 72 bits in our case, without changing the architecture. It works at memory depths of 2 to 32,000 words. And it also works with a variety of pipeline depths, from 8 to 16 pipeline stages, all without any fundamental change. So I'm going to walk through the design process. How do we get to this? So I'll begin with a high-level view. So we started with the simplest possible processor on an FPGA. So here's almost a basic von Neumann machine. We have our memory, which is entirely implemented in block primes on the FPGA. Provides us 3 pieces of data, 2 data operands, A and B, and an instruction I, which tells us what to do with them. Feeds it all to an ALU, which then writes back a result to the memory. Straightforward. Key point here is we've unified the registers and the memory. So you can think of the system as either register only or memory only. That division of address space doesn't exist anymore. To highlight that a little more, I'll compare it to a classic RISC pipeline. So here's again our basic Octavo, and here's your basic 5-stage pipeline: instruction memory, register file, execution, data memory, and write back. So the ALU and the execution stage are very basically identical. Take data, take instructions, do something. All the memory stages after that, register, data, and instruction, are all mapped into the block RAMs into a single memory object. So I hope that clarifies exactly how we this fundamental change in assumption. So we unified all memories, which means that now there's no loads and stores, and there are no immediate operands. They're no longer necessary, and that'll have interesting consequences. But this is easy to say. The question is how do we pipeline this to get good performance out of it? So the approach we found to guide us is something we call self-loop characterization. The idea is actually quite simple. We simply take a module that we want to know how to map well and connect its outputs back to its inputs. The reason we do that, though, is then we account for the FPGA interconnect as part of the module's operation, as opposed to simply having input straight through and output. We then take the loop path and we pipeline it to absorb delays. We let optimizations like register retiming work. So this worked pretty well and guided us, pointed out to us other limits to designs than raw delay on an FPGA. Mostly we hit up against documented, but we didn't expect to reach them, minimum clock pulse widths. So for example, the DSP blocks run at 480, not because of delay limitations, but because you can't clock them that fast. The spec sheet says so. Similarly, the block RAMs have a delay, internal delay that's actually quite low, but we can't clock them faster than 550 for internal reasons. This is also documented, but self-loop characterization kind of brought that to the fore. So I'll show you an example by doing the self-loop characterization of a block RAM. And we got some surprising results. So if we take a single block RAM with a registered output and we simply loop it back onto itself and then measure how fast this can run, you'd expect that it would run at 550 because there's nothing there, but actually it only runs at 398. This is the routing overhead. The RAM is not connected directly to the fabric. It has to get out of the RAM block onto global routing, go all the way around on global routing, and then back into the RAM. So to try to mitigate that, we add one extra stage of pipelining, just registers. And that jumps us up to 656 megahertz, above our 550 megahertz goalpost. Now, that's nice for a single one, but if you extend that, say you make a deeper memory, so you have multiple block RAMs, you've got to connect them with a bit of logic. So say you do that, you add one extra stage of pipelining on the outside, you're at 531, not quite fast enough. Add a second one, and you're at 710 megahertz. But again, we can't clock faster than 550 because of clock limitations, not delay. So there's a lot of slack available this way, with not much pipelining. Now remember that when we're using multiple block RAMs, they're not together as a block, they're actually spread on the FPGA. So really what we're also measuring is the delay and overhead of going from one block RAM to another. So the single block RAM example is equivalent to having output of one block RAM feed directly into another block RAM with one pipeline stage, it's having one register in between. And similarly, if we have deeper block RAMs, it's like having a bunch of block RAMs put together, two pipeline stages, and another bunch of block RAMs synthesized together as a larger unit. So the result generalizes that way. So eventually we learned we must connect block RAMs with registers in between. This comes up later in the design. So the memory, I'll go into how we constructed the memory in Octavo. So we basically have a triply replicated memory, a memory in three parts, you could say. There's the instruction memory, which simply provides instructions. There's the A memory, which provides one data operand, and some of its addresses are memory mapped to input and output I/O lines. We have the B memory, same thing, provides another data operand. It also has I/O mapping. They all receive the same result from the ALU, so the contents are actually identical across all this. It's just a plain replicated memory. It behaves as a scratch pad. There's no external memory, no bus, no caches. We have 2, 4, 8 I/O lines, and we can still do this while exceeding our goalpost of 550. The counterpart to this is the ALU. Now here's the big high-level block diagram. I won't get into the details. Suffice to say that it's got 4 stages of pipelining. It's fully pipelined, and it never stalls. It does, addition, subtraction, logic operations, and multiplication, but I'll focus on the multiplier because that one was a little tricky. It takes 3 stages. It's implemented using the DSP hardware blocks, but the DSP hardware blocks, we already know, only go to 480. Now our goalpost is 550, so we've got to overcome that. In a nutshell, one multiplier DSP block is wide enough to do what we want to do forward multiplication with a double wide result, but it's too slow. One of them goes to 480, even if it's pipelined internally. So what we did is we took 2 multiplier blocks and we made them work at half speed, and we fed them data in alternation. The net result is that we can now use 2 of them to do forward multiplication at 600 megahertz if we so wanted to. So having high-speed memory, flexible memory, high-speed ALU, we put it all together. So I'm going to go and describe the whole Octavo architecture at a high level. So we begin with the pipeline. It has 10 stages. It's actually 8 stages, but there's one special case path that has 10, and I'll get to that later. There's no result forwarding or pipeline interlock. It always goes straight through. And it's a scalar, single issue, in-order processor, but it's multi-threaded. So just to set the stage. So we start with the instruction memory, pretty easy, indexed by PC, provides a 3-operand instruction, and it's only on-chip block RAMs. That eventually feeds to the A and B operand memories, get the operand addresses from the instruction, provides the data to the ALU and the controller. Also, entirely made of block RAMs, some of the addresses map to I/O ports. That's how we get data in and out of the system. Now, in between them are some empty pipeline registers. Now, remember our results from self-loop characterization? This is where they come from. So we use the pipeline registers to avoid an odd number of stages so we can balance pipeline lengths. But we need at least 2 here in this case to separate the block RAMs so that we get the maximum speed. This is, again, what self-loop characterization told us. It's really unusual, it was unexpected, but it's an essential design constraint. We can't get away from it. So, moving along, after the memories, we have the controller, which simply receives the opcode, some source destination operands, decides the branches, and provides the next PC to the instruction memory. Pretty straightforward. And then after that, we have the ALU finally, all 4 stages, takes the opcode and data, crunches the numbers, writes the result of all the memories, so A, B, and I. In this, the longest mandatory loop is 8 stages long. So it's the A and B memories and the ALU. So to avoid stalls and dependencies, we simply decide to fill it with 8 separate threads. So while threads 0 and 1 are reading their operands from the memories, 2, 3, 4, 5 are going through the ALU, and then 6 and 7 are writing their results back to the memories at that time. So these 8 threads can all proceed independently without ever stopping. There's a special case loop, 10 stages. Now this one is the instruction memory through the ALU. This is because of those pipeline registers. It actually does not affect most computations. Its only effect, in a nutshell, is to add a delay slot to subroutine and loop code. That's about it. So now, having explained how we got to it, the logical design, I'll show you some actual measurements. So our framework was just Chorus 10.1, targeting the fastest Stratix 4. We optimized and placed for speed. We averaged speed over 10 runs with different random seeds, the usual. We varied width, memory depth, and pipeline depth. And then we observed the resulting frequency, the area, and the area density. This will be an interesting thing I'll talk about last. So the maximum operating frequency, here's the graph. Let me describe it. So the y-axis is the megahertz. Upper is faster, so 200 to 650 megahertz. The x-axis describes the word width of the entire system, so 8 to 72 bits in this case. The dotted line here is at 550 megahertz. That's the block RAM hard limit. So no matter how well we do, this is actually as fast as we can realistically clock the system. Anything above that is pure timing slack. So I'll highlight also, the NEOS 2F is on this graph. So there it is, it's 230 megahertz and 32 bits wide. The nearest equivalent Octavo design is up here. It's 36 bits wide and it runs at 550 megahertz. It's a little over twice as fast, but it's not really a fair comparison because they're very different architectures as you've seen. Also, that little quirk in the graph here is actually a CAD anomaly from Quartus. For widths of 38 to 54 bits inclusive, for some reason, it couldn't map the multipliers efficiently to all the DSP blocks, requiring extra logic and giving us a performance penalty. The anomaly affects all designs, and we can see it here if we look at the 12-stage version of Octavo. where once we hit the anomaly, our speed drops, and once the anomaly disappears, we go back up again. However, since it just manifests as extra logic, we can simply add more pipeline stages, 14 or 16, and then we're back on the expected frequency curve. So we can bury the inefficiency with enough pipeline stages. This was one unexpected result. Now, area density. So here is a block view of a 72-bit wide Octavo with 1,024 words of memory. And, everything in the purple shaded area is the processor itself and its memory. Anything on the outside is a test harness and we don't count it. This one, to the same scale, is a 72-bit Octavo with 4 kilowords of memory. The dark columns you see are actually the block RAMs used, and the dark purplish areas over here are the actually used logic to various degrees. So you can see that the first version here uses its area, its rectangular area, pretty well, while this one actually leaves a lot of the area empty. So here's the actual processor logic, and then all this area here around the block RAMs is actually unused. So the 1024 word version uses about 67% of all the logic in its area, and this is apparently typical. If you try to force quarters to pack things and restrict them to an area, it will seem to hover around 65–70% of the ALUTs on the inside. Whereas this one is only using 26% of all the logic inside its area. This suggests that there seems to be a sweet spot at around 1,000, maybe 2,000 words of memory, where the area required by the block RAMs and the logic that uses them all fit together in a nice small area. So we're using the hardware efficiently in space. So given all that, what we learned from all this is that we can hit the block RAM Fmax with a soft processor. We have 8 threads, took 10 stages, and in many cases we can reach 550 megahertz, which is as fast as we can run it. Self-loop characterization of our modules helped us reason about the pipelining and do not too little, not too much, put it where it's required. It also gives us the true operating envelope of a module on an FPGA. It takes account for the interconnect. We also learned that Octavo, it spans a large design space. It's not a single quirk design that happens to work well at a particular configuration. It spans a large range of widths, depths, and a number of stages without changing the architecture. So this suggests that we should really consider FPGA-centric overlay architectures if we want to go and get more performance and more efficiency out of the designs. So the future work, I've described one processor. Our future work is basically we're going to try to create a 2D mesh of Octavos, tightly coupled, to try to see if we can extend this efficiency and this performance to the whole FPGA fabric, and then if we can find a way to map applications to it. And that's it. Have any questions? Yes, please.
Three quick questions.
Okay.
First, did you turn on, you mentioned the physical synthesis. Were you using that throughout your whole flow? Register retiming?
Oh, yes, yes. Register retiming is used. Like, the optimizations are pretty much turned up all the way. The only exceptions are the processor was actually restricted to its own design partition and its own logic block, spatial partition, so that the test harness would not get sort of blurred in, or registers in the test harness wouldn't get retimed into the processor to artificially increase performance. So that was taken care of. Internally, however, we register retime. We do whatever we want. Okay. Any other question?
Yes, so about the block RAMs themselves, in addition to the pipeline registers, extra ones you added, did you also dual register internally the block RAMs themselves, meaning input register, output register?
Yes, they're registered, and they use the forwarding logic that gets automatically created. So internally, the block RAM, if you write and read to the same address, will return the new data. This is actually necessary to get the top of the operating envelope, that 550 megahertz. There's internal reasons, but I won't go into that.
Okay. And finally, so is the only restriction now 550 megahertz because of the block RAMs?
Yes.
So couldn't you theoretically do the same thing you did with the DSP blocks and make them run half the speed when you put it into different ones?
I thought about that, but it gets really complicated because the DSP block is pipeline, so it doesn't really store state over time, whereas the memories do store state over time. So if I suddenly start ping-ponging between two memories, it means that a future instruction has to be just on the right even or odd cycle to fetch the data that was written by another one. I suppose you could do it, but that sounds like a scheduling nightmare. Yeah. Yes?
So you said that you had to change your ISA for this particular processor. When you did that, did the number of instructions increase, decrease, or?
Decreased. So we didn't preset the ISA. We kind of just figured out the architecture and then saw if we could have an ISA that was general purpose on it. If you compare it to, say, the MIPS ISA, it decreases a lot because all the variants that do load store are gone because there is no meaning for load stores here. And all immediate operands also disappear because addressing is registered direct. If you want a constant, you keep it in memory and you can just access it directly with no penalty.
Right, but for a particular program, the number of instructions that need to be run, that will change. And does that one increase or decrease?
Looked at it a little bit, did a few test loops and all that. I don't have an actual benchmark, but from initial observations and initial tries, for straight line computation, it's probably going to remain the same or very close to. If you have loops involved, long story short, your preambles are going to get bigger. The loops themselves, however, there are tricks you can do that could reduce the overhead of the loops significantly. But we haven't looked into that deeply. Like this is a whole other kettle of fish I'm not touching in this talk.
But just as a follow-up to that, rather than replicate these things as your future work, shouldn't that be your future work? To really understand what your performance penalty is cycle count-wise?
Well, it'll be part of the work, but there is no reason to believe that there's going to be significant penalty. Because if you take, again, the MIPS ISA as a reference, and if you take out all the loads and stores and all the versions of instructions with immediate operands, all you're pretty much left with are a few logical operations and or XOR. You're left with addition, subtraction, multiplication, and that's it. That covers most everything. Like, I thought about this really hard. I had difficulty believing it, but I looked at the MIPS ISA, I looked at this ISA, and it does seem to cover it up. So if you're just doing straight computation where you're just moving data, flipping a few bits, and then reading and writing from memory, it's the same code, effectively.
With the requirement that it be multi-threaded 8 ways.
Yes, you have to run 8 separate threads to get everything out of it. But then again, this is not different from a GPU. Yes?
I guess maybe one follow-up on that is that, I mean, you've also removed the forwarding logic to get more speed,
Yeah.
which will hurt you in some cases where you can't separate operands as much, which I think you'll have to run programs to try to figure out.
Oh, if I have a dependency?
Yeah, I mean, on a program where you can structure it such that you have no dependencies, that it won't hurt you. But an interesting question is, well, what applications have that structure and what applications don't? You know, how much does that hurt you? Well, some applications it will hurt.
Our initial premise was to do data parallel work. So assume lots of separate threads working on more or less independent data, like a GPU nowadays. So that would be the ideal case. Now, the compiler can, however, do whatever the heck it wants. The threads here are notional. You could, in theory, just schedule the instructions and knowing there's like an 8-cycle dependency, and if you can do it, you can do it. But
I guess that's a suggestion for follow-on work too, to try to clarify like when you look at a few real applications, like do they meet that perfectly? Do they, some of them meet it perfectly, some you lose some efficiency? It seems interesting.
it'll depend on the application. It'll also be affected by going multi-core, because all of a sudden now you can think of, well, I can write it here, and I can read it here, and the number of cycles here I can take into account. We're getting there.
I have one other question, which is, so you've changed the way that you're interpreting register files and memories.
Yeah.
And I think in a way, I mean, it's still related to register files and memories, I think, but you have unified it. How would you hook up to an external memory? Is that something that you don't envision doing because of the applications you want to target? Or is it something you do envision doing, and if so, how would you do it? Like, I've got an off-chip DDR3 memory bank. How do I hook up to it?
You'll have to think about it as if the memories on the Octavo are scratchpad memories. And any external memory has to be addressed by software. So you could, for example, at the edge here of all these I/O lines, tack on a DDR3 controller and then make requests to it and then access the external memory that way. So the external memory is now, the programmer or the compiler has to manage it. It's no longer transparent. That's the difference. but there's otherwise no restrictions to what you want to do.
So what instructions would you use without load and store? Like what exactly? You have certain memory addresses that hardware would interpret as a command to the DR3?
No, software would. What happens is that you have your entire memory, and some of the addresses, like say near the end, map to I/O ports. So your operation would, any operation, would simply have as a destination operand, if you wanted to write, that I/O port that would go out, be interpreted by whatever hardware is at the other end, say a DDR controller. And then when you want to read it, you read from the same I/O port, and you get your data back from the DDR controller.
Sure.
And there's no, and since all instructions can access all memory as two source and one destination, you can do this with any instruction, except flow control, but that's complicated. Yeah. Yeah?
So, thinking of a potential application for this processor, let's say you have a stream of data that you want to work on.
Mm-hmm.
Could you envision a way, is there like a free port on that block RAM where you can inject data in and operate on it as if it was part of the scratch pad memory, and then pull data out
Yes.
in sort of a flow controlled manner so that it works as a stream processor?
Yes, totally. Now, the I/O blocks, the I/O ports in the memory are addressed just like memory. They're completely memory mapped, completely transparent. They behave as any operand to an instruction. There's no difference. So that means if you want to say, for example, feed data in here and then stream it through and get it out of the other end, all you do is whatever instruction starts the process of computing with the data, reads from one of the I/O ports, crunches the data, writes it to the output I/O port, and that's it. You're streaming. In fact, it's better than a conventional processor, because a conventional processor you can only do one read or one write per instruction. Here, since the memory access and by extension the I/O access are operands, you can do two reads and one write, and they could all be I/O if you want to. And you can do that every single instruction. Does that answer your question? Oh, yeah?
So I guess I have a follow-up question for the external memory access.
Sure.
So suppose you're doing a read,
Yeah?
and the thread has to wait for the data to come back.
Mm-hmm.
It takes long, so it has to stall
Yes.
somehow.
Yes.
So I probably missed it. I don't know how you, I guess your thread is at pipeline level rather than like a real-time, OS.
No, it's a pipeline. It's fine-grained multi-threading.
Yeah, which means the other thread is going to store as well, is that right? Eventually.
No. Say, for example, you have one thread that is doing something to access external memory,
Right.
and then it has to wait. The other threads are oblivious to it. They just keep going. Now,
Yeah, but the question here is that your instruction fetch, right? Do you share the same instruction fetch unit? How big is your, let's say, instruction window, right? So, because if these threads kind of out of sync with each other in
Mhm.
terms of which instruction you're executing, right? So these, I think you refer to like a GPU, right? I think the GPU, when you have, what do you call it? You have
warps?
yeah, warps, exactly. So
Mhm.
if the warps essentially executing the same instruction, so they're not
Yeah.
out of sync with each other.
No,
right?
here these are all separate. They execute, each thread has a separate program counter, and the controller feeds each thread's
So it's completely different streams, right?
completely different streams.
Okay, okay.
So, to answer your initial question, if say a thread wants to access external memory and has to wait for it, there's two ways to deal with it. Right now, there is no hardware support, meaning that you would have to write a small busy wait loop to send the request to a DDR controller, and then that thread will then sit in the loop until it receives the data and continue. Then one of the things we're going to work on is adding I/O synchronization hardware, where you have a simple one-bit handshake. You do, say, you'll send your request to the DDR controller, then the thread will try to do a read from the port, and if the data is not there, the instruction will be converted to a no-op, and then the original instruction reissued the next time. The controller just won't increment the PC. So the thread will just sort of stall at the instruction level until the memory request can be fulfilled.
Sure.
So that's the next step. So that eliminates the busy wait loop. Yes?
I have a couple questions about the ISA.
Please.
What's the word width, the instruction width, sorry? Is it full?
It's the full word. The instruction always takes up the full word.
Mm-hmm.
It is structured, however, as the opcode, which is always 4 bits.
Yeah.
And then the remaining bits are basically divided into 3 chunks, and then each operand can address that many words. So my favorite case is 36 bits wide, where the first 4 bits are the opcode, The remaining are divided into 3 groups of 10, and we waste 2 bits at the end, but that means we can now address 1,000 words.
Yeah.
Each operand can address 1,000 words.
Right, so my question would be, is there a particular reason that you ruled out some of these other addressing modes? Especially immediate modes, for example. It seems like a waste to have to go fetch a second word just to hold a constant that's likely going to fit
No.
in your 10 bits.
No, there is no waste. The immediate modes aren't required. The addressing is register direct, which means, say for example, you want to increment a memory location by 1. What you would do is you would store the constant 1 somewhere in memory, doesn't matter where, and then your opcode, your instruction would basically be add, destination is your increment, your accumulator, first source is your accumulator, and then the third source is the memory location that contains the 1.
Sure.
And that immediately adds 1 to that memory location. There's no overhead.
No, I'm not talking overhead. I'm talking when you have 1 kilobyte of RAM total, that is storing all of your constants in that.
Not 1 kilobyte, 1 kiloword.
Right, but the same thing, right? Rather than having an instruction that encodes add 1 to this thing directly, you have an instruction that says go fetch a 1 from some other memory word which is now unusable for other purposes and add that.
Yes.
And since encoding the 1 costs less bits than encoding the address of the place that contains the 1, and you have a couple extra bits in your ISA that you could use for things like this, it seems like a bad trade-off for an embedded system.
No, I think it's an excellent trade-off. Adding immediates would decomplicate the decoding, and we have to keep it fast. And we don't want to add as more pipeline stages than necessary, because that means we need more threads to fill it, and then that means less memory per thread to work with. Also, that 1 in the memory is not fixed to that 1 thread. It's usable by all threads. And how many constants are actually in the core loops of a program? Not that many. 1, 0, plus 1, plus 4, and then you start to run out. So you use maybe 10, a dozen memory locations, and it holds all the constants you'll ever need.
I was thinking more of branch offsets. Right?
Addressing is direct. So that means if you want to, when you specify a target destination, it's actually in your operand, because each operand can address the whole of memory. So you never have to fetch the memory, your target of your branch from memory. It's in your instruction already.
So that's immediate.
That would be an immediate, yes. Technically, that's immediate.
Okay, I think we better end this interesting discussion. We can certainly carry on after lunch, and thank you very much, Eric.
Thank you.